All right, so our focus this morning primarily is we're going to do two things. We're going to first look at concentration, and this should largely be review for us. We've covered concentration in Chem 1, or we've talked about most of these units in some form or fashion before. So last semester, we talked a whole lot about parts per mass. We looked at mass percentages. We looked at um, parts per million and parts per billion when we did the water lab. We didn't talk a whole lot about parts per volume, but the idea is essentially the same, only substituting milliliters in for the grams. And we spent a whole lot of time on molarity. It's those last two units, the molality and the mole percent, or its close cousin, the mole fraction, where we do the same calculation, we just don't multiply by 100. That is where some of the important calculations that we're going to be doing today and in this chapter are going to come from. So let's just take a quick walk down memory lane here and talk about some things that we have seen in the past. So we have seen parts per mass before. In parts per mass, we are looking at the mass of the solute divided by the mass of the solution times 100%. And if you remember back to 105, these are common definitions of parts per million and parts per billion. So 1 gram per million, 1 gram per a billion, or if we want to standardize to the gram, 1 microgram or 1 nanogram. We also talked about, from a calculation standpoint, taking that same fraction and multiplying it by a million or by a billion for parts per billion. The idea is effectively the same. And this is why percentage can be referred to literally and truly as parts per 100. It's the fraction, and the per whatever is the number that we multiply by. Parts per volume, we don't get a whole lot of traction on these usually. Most of the solutes that we are dealing with in this class and in Chem 105 are solid in nature. And so measuring their volume doesn't really make a whole lot of sense, because it's far easier to measure their masses, and from their masses we can determine their moles and so on. Where this comes in is liquid kinds of solutions. If I want to measure out ethanol in water, parts per volume is a great way to do it. And by most accounts, the easiest one is just the parts per 100, the volume percent. This is the metric that the alcoholic beverage industry runs off of when they produce ABV, alcohol by volume. Multiply that number by 2, you have the proof label on your harder spirits. Parts per million, parts per billion can be used as well. We put the V term on there usually if we're talking about something that is, again, volumetric. Although in most cases, if we're talking about parts per million and parts per billion and the solution is aqueous, what we'll often see is kind of a blending of these two, where we can talk about, for an aqueous solution, parts per million is sometimes defined as micrograms per liter. Why per liter? Well, a liter of water would weigh 1,000 grams. So we could scale and then scale again. So milligrams per liter, micrograms per liter. We see these again because the density of the water is 1. We talk about molarity a lot. Molarity is the easiest concentration unit for us to use. We use it quite often because, well, it's really convenient. Moles are useful. They help us with chemical reactions. Liters are easy to measure volumetrically. We have graduated cylinders, pipettes, burettes, lots of different directions that we can go. The primary issue with molarity, why it cannot be used universally in all situations involving chemical processes, is this. There is a temperature-dependent component of molarity. Moles are not temperature-dependent. Moles are related to mass, mass is related to matter. Matter doesn't expand or contract. But volume does. Thermal expansion is a real thing. And even in liquids and solids, it's minute, but it's enough to notice in certain kinds of situations, especially if we're comparing extremes. And from that standpoint, what that means is that molarity changes with temperature. Because even if we are off by just a matter of a couple of milliliters, if I'm comparing a solution at 10 degrees Celsius and a solution that it's at 90 degrees Celsius, they're both still aqueous solutions. But I can't guarantee that the difference in volume for the water at 90 degrees versus 10 degrees isn't enough to change the molarity in the last couple of sig figs, especially if we're talking about dilute solutions. So when it comes to looking at concentrations where we have to explore the possibility of temperature change, we need a different unit. And the different unit that we are going to look at is something called molality. Now, molality has a lot of the same advantages to it that molarity does. Moles of solute is in the numerator. From that moles of solvent, we can do things like stoichiometry. We can measure out our solute in terms of grams. The difference is that the denominator here, kilograms of solvent, well, that's not going to change with temperature either. Like I said just a minute ago, mass is mass. It's all related to matter. Matter doesn't expand, well, matter does not change in value based on temperature. So molarity and molality have a lot of common ground between them. And they can get a little bit confused. they can get a little bit confusing because we use the same letter to stand in for them. Capital M for molarity, lowercase m for molality. But the difference is utilization. We're going to use molality almost exclusively when we're looking at things where temperatures and temperature extremes are going to be involved. The last unit, mole fraction. Mole fraction is abbreviated by either a large uppercase X or most commonly it's the Greek capital letter chi, which doesn't come through on most software packages. So just be aware that if you see it, that and it looks kind of like a funny tilted X, that's why. But for mole fraction, it's a literal calculation of the number of moles of whatever it is that we're interested in, divided by the total moles of everything that's in the solution. And where we have to be careful with mole fraction is almost everything up until this point has focused on the solute. Solute has been in the numerator for every single unit that we've looked at thus far. With mole fraction, that's not always the case. One of the applications of mole fraction is vapor pressure lowering. And for that, we're interested not in the mole fraction of the solute, but rather of the solvent. Because we want to see how much the solvent is impacted, which means we need to know how much of the solution is solvent. So let's take a look at a question here where we're kind of asked to do a variety of things with concentrations. So I've got 75 grams of acetic acid. I've dissolved it in 45 grams of water. And the total volume of the solution after everything is mixed together is 309 milliliters. The first question is this: what is the molarity? What is the molality? What is the mole fraction? And what is the density? Well, the last question is actually the easiest to answer because we know that density is equal to mass of solution over volume of solution. And well, we've got that already basically. The mass of the solution is 75 grams of acetic acid and 245 grams of water, all in 309 milliliters. 75.0 plus 245.0, we have 320.0 grams in 309 milliliters. So to 3 sig figs, that would be 1.04 grams per milliliter. Kind of taking us back to a chapter 1 kind of concept here, but we want to make sure that we don't lose sight of the fundamentals. And one of the reasons we don't want to lose sight of that fundamental in particular is that if we are asked to convert between units, density is one of those things that is an absolute necessary component. So what about these other three, molarity, molality, mole fraction? Well, for those, we're going to need some information. And so what I'm going to do is before I actually go to settling this, let's calculate the moles of each of our components here. So away. 75 grams of acetic acid. Molar mass, I've got hydrogen 1.01, carbon 12.01, and there are two of them. Hydrogen 1.01, and there are three of them. And oxygen 16, and there are two of them. 60.06 is my molar mass. And so the three significant figures, 75 divided by 60.06, 1.25 moles. And for the water, 245.0 grams of water. Molar mass of water, we probably know this by heart, 18.02. 2 hydrogen, so 2 times 1.01 plus 16. So 18.02. 245 divided by 18.02 to four significant figures, because we have four in this mass, 13.60. Now, why do this legwork early? You know that you're going to need everything. So it makes sense in this case to kind of do all the legwork now, and then you just have to plug the right values into the right equation. So for molarity, capital M, is equal to moles of solute divided by liters of solution. The moles of solute, the acetic acid, 1.25 moles. And the liters of solution, 309 milliliters divided by 1,000 is 0.309 liters. 1.25 divided by 0.309, we get 4.05 molar acetic acid. And so, just as a reminder, when we're doing calculations of concentration, three things need to be in every single measurement. You have to have the correct label. So you got to have the correct number, rounded to the correct number of sig figs. You have to have the unit, molarity. And you have to have what that is the concentration of. In this case, acetic acid. We know far too well solutions can be made out of multiple things. And so if we're not explicit about our labeling, we could end up making mistakes when it comes to interpretation. All right, for molality. Molality is lowercase m. It's moles of solute over kilograms of solvent. This part's the same, 1.25 moles. Kilograms of solvent, 245 grams divided by 1,000 would be 0.2450 kilograms. So 1.25 divided by 0.245 would be 5.10. So there's my number, rounded properly. My unit is molal, lowercase m, and my substance is acetic acid. for mole fraction. Mole fraction is equal to the moles of the thing that we're interested in, which in this case is water, divided by the total moles. Well, the moles of water are 13.60. And the total would be 13.60 for the water, plus 1.25 for the acetic acid. And so from a labeling standpoint, mole fraction does not have a unit because the units have canceled. This is moles divided by moles. What we do to label is we would put the substance as the subscript for the mole fraction. So chi sub water would be this value. And so 13.60 divided by the sum of 13.6 and 1.25, which is 14.85, to four significant figures is 0.9158. And so the way that we would express this is that the mole fraction of water is 0.9158. Now we could do a similar process with the mole fraction of the acetic acid, but just like we do with calculations of mass percentages, we also recognize that every part has to equal up to the whole. And so if this is a solution of only two components, the other component has to be the acetic acid. So we could calculate the mole fraction of acetic acid as just being 1 minus this, because that's the only other thing. And so it'd be 0.0842. All right, any questions with just kind of using the definitions to solve calculations of concentration? Okay, so let's get into where things can get a little bit complex for us. For one, because they share a common denominator, molarity and molality can be interconverted between each other if we know the density of the solution. Now, this schematic tells us kind of the pictorial way of looking at it. What I tend to do, and what this is attempting to show really, is that when it comes to molarity and molality, the easiest thing to do usually is to separate the components from each other. So we know that really the difference between molarity and molality is not in the numerator, because the numerator is the same. It's in the denominator. If I'm looking at kilograms of solvent, because I'm looking at molality, I need to know how to turn that kilograms of solvent into liters of solution. And the process for doing that basically is I need to figure out the number of the mass of the solute, add that to the mass of the solvent, use density to convert that mass into volume. This is a schematic showing specifically the conversion from molarity to molality. And what we see is that we need to convert the liters of solution into kilograms of solvent. How do we go about doing that? Well, using density, we're basically just going to implode this fraction. We're going to take that 1 liter of solution, convert it into grams using the density, and then taking the grams of the solution and subtracting off the grams of the solute based off of the number of moles that were there, I can figure out the kilograms of solvent. Maybe it would be easier to just run through a calculation just to kind of see what it is, what we're talking about with numbers rather than with pictures. Okay, so we have a solution that's 0.194 molar in nitric acid, and its density is 1.1 grams per milliliter. So what I'm talking about here is we know that molarity, in this case, tells us that we have 0.194 moles of nitric acid in 1 liter of solution. That is the definition of molarity. Now, what we want to do is to figure out the molality. We need moles of nitric acid in kilograms of water, the solvent. The heart of this calculation is to try to do as little as possible. And so if our molarity is predicated on 0.194 moles of nitric acid, we're going to do the same. We're going to have 0.194 moles of nitrate of nitric acid in our molality. What we need to do is we need to convert the 1 liter of solution into kilograms. So 1 liter is equal to 1,000 milliliters. That's an exact conversion. So if I have 1,000 milliliters of solution, the density of the solution says that for every 1 milliliter of solution, I would get 1.10 grams. And so this tells me that I have 1.10 times 1,000. I have 1,100 grams of solution. What I need to do is I need to figure out how many of those grams are water. And the easiest way to figure out how many of those grams are water is to figure out how many of those grams are not water. This is where the 0.194 comes in. 0.194 moles of nitric acid One mole of nitric acid weighs, see, molar mass. I need hydrogen, 1.01, nitrogen, 14.01, and oxygen, 16, but there are 3 of them, so times 3, 63.02. So 0.194 times 63.02, three significant figures, 12.2 grams. So in our solution was 1,100 grams. 12.2 of those grams belong to nitric acid, which means that the remainder must belong to water, since those are the only two things in the solution. So my mass of water is going to be 1,100 minus 12.2. Here's where sig figs are going to come in and perhaps be a little bit interesting. Since our density was only known to three significant figures, the tens place is the last significant digit in the water. And so the calculator says 1087.8. We are going to have to round that to 1,090. And since we're interested in kilograms of water, not just grams, we need to divide by 1,000. So 1.09 kilograms is the result. So 0.194 divided by 1.09. My molality to three significant figures is 0.178. 0.178 molal nitric acid. The process of converting molarity into molality is not a terribly difficult one. The places where we get confused are usually in how we handle that density. And that's why we have to remember density is a description of the solution, not the solute. It's a description of the solution. And the reason that matters is because I've seen this, when we used to teach this in Chem 105, saw it in Chem 105. When we moved it over to Chem 106, still see it in Chem 106. The misuse of density, where if you're not sure what to do, you end up taking, I've got 1.09 kilograms of water and I know the density, so I'm going to just turn that into liters, and there I go. Or in this case, I figured out the number of grams of nitric acid, and now I'm going to turn that into milliliters, and there's my answer. And it doesn't work out well. Having an understanding of those definitions makes a really significant difference in terms of the difference between getting these right and not getting these right. So any questions on this before we move on to the next thing? All right, well, what if we have to go the opposite direction? What if we have to go from molality to molarity? Well, the process is pretty much the same. Molality would tell us that this solution, 1.92 molal ferric nitrate, iron 3 nitrate, is going to be 1.92 moles of iron 3 chloride in 1 kilogram of water. And what we need to turn this into is moles of iron 3 chloride in liters of solution. So the process is going to look very, very similar to what we just did, but effectively the reverse. So the one thing that is common between them is we are going to have to convert the moles of iron 3 chloride into grams. 1 mole of iron 3 chloride. Iron is 55.85. Chlorine is 35.45, and there are 3 of them, so times 3. 162.20 for every mole. I multiply that by the 1.92, and I get to 3 significant figures, 311 grams of iron 3 chloride. So that part we had to do in the other calculation as well. We had to convert the moles of the solute into grams. This is where it flips around and is different. Because in the last stage, what we did was we took that value, subtracted it from the kilogram or from the grams of solution to find kilograms of water. Basically, all we're doing here is reversing the process. We are going to add this to our kilogram of water. Kilogram of water weighs 1,000 grams. And since this 1 kilogram is defined, it has infinite precision. So we add these together, we're going to get the exact number of decimal places that we had from our calculation. 1,311 grams of solution. Only thing left is to convert that grams of solution into volume. This is where the density comes in. 1.07 grams of solution is equal to 1 milliliter of solution. And then we want 1,000 milliliters to make 1 liter, since we have to deal with liters of solution here. So 1,311 divided by 1.07 divided by 1,000, and we get to 3 significant figures because of the density, 1.23 liters. So our denominator is 1.23. The numerator is the same, 1.92 moles. Our molarity to 3 significant figures is 1.56. So this calculation conversion is not that bad if you understand what it is that each of the definitions mean and how to easily navigate how to go from one to the other. You're always going to have to convert the moles of solute into grams. It's a matter of what do you do with it. Am I building solution from solvent? Or am I trying to figure out which component, the value of each component? That's basically what I'm asked to do. Questions in this example? So the other major kind of calculation that you have to do with concentrations is one that you're already quite familiar with, and that is the dilution. Just as a reminder, the dilution technique here, the equation, C1V1 is equal to C2V2. This works mainly because when we do a dilution, the number of moles does not change. Um, kind of central idea of solute does not change. We're just adding more water. And so because of this, we can actually simplify the calculation of dilution with this. C can represent any concentration unit. So with the exception of mole fraction, you can't use mole fraction here because obviously mole fraction would change if I added more water. I'd have more moles of water now. But aside from that one, percentage, mass percent, volume percent, all those would change just fine. Molarity, molality, they would work out okay. Basically, any of the volumetric ones would work out here. So molality probably wouldn't work as well, unless the solvent was water. But the volume can be any unit as well. Liters, milliliters, it works out okay. So let's go ahead and take on a review question here. How much concentrated 10 molar nitric acid is required to prepare 2.25 liters of dilute 3.3 molar nitric acid? All right, so setup for this should be relatively simple. Our initial concentration is the 10 molar, and we don't know how much we are going to measure. Our final concentration is 0.3 molar, and we know that we need 2.25 liters of that stuff. So if I divide each side by 10 molar, point 0.3 times 2.25 divided by 10 is 0.0675 liters, which if we converted to milliliters would be 67.5. Any questions there? Okay, let's go ahead and take our break then. Come back in 10 minutes and we will start talking about applications of this towards solutions with colligative properties.